Good evening. My name is Hiram Muscabi. I'm serving as branch assistant for STEM training. Welcome to this month's Tech Talk, Weather Radar, presented by Lindsey Richardson and Autumn Losey-Bailor. Tech Talks are sponsored by the United States Coast Guard, the United States Coast Guard Auxiliary, and the Boy Scouts of America Sea Scout program. Tech Talks are held on the fourth Tuesday of the month at 2100 Eastern Time. Next month's Tech Talk is on September 26. Just a reminder, this Tech Talk is being recorded and will be posted on the Sea Scout and Aux Scout YouTube channels. Please subscribe to the YouTube channels and share it with your shipmates that could not join tonight. Remember that questions can be posted in the chat box. The recorded Tech Talks make an excellent training for your shipmates in your ship and auxiliary flotilla. I would like to introduce our subject matter experts, Lindsey and Autumn. They're colleagues from my colleagues from the National Weather Service, and they're located in Norman, Oklahoma. Ladies, take it away.
Thank you, Hiram, and welcome everybody to this wonderful Tech Talk. We'd like to talk about the Radar Operations Center, which is seen here. This is our main campus, and we took this picture from one of our radar towers so we can oversee all of our lovely little buildings where we get to work every day. So before we really get into everything, let's actually practice being a radar. And what I want everybody to do is, when prompted, scream the word radar until the stop sign appears, and it lasts about 3 seconds. Ready? Go. Radar! And now sit back and listen quietly for the rest of the presentation. The idea is that a radar sends out a signal for a really short amount of time and then listens for a long amount of time. So we can simulate that with our presentation here. As Hiram introduced already, we are your tour guides to the Radar Operations Center. We both are computer scientists at the Rock, and we both have backgrounds in meteorology. So we spent a lot of time actually at the National Weather Center, shown here at the University of Oklahoma. We had a lot of classes here, and one of the branches of the Radar Operations Center is actually part in this building. So who is the Rock? Well, we are actually located in central Oklahoma, as Hiram mentioned, and we are a central group that maintains the National Weather Radar fleet for the entire country. And our mission is just that. We are there to support the radar from everything we can do: software maintenance, engineering support, special level requests, expert techniques, things like that. And we are a tri-agency funded group by the Department of Commerce, Department of Defense, and Department of Transportation. So that makes it a little unique in that we have these 3 agencies all working together to make sure their missions are met with weather radar. We have support from multiple different types of radar systems at the Rock. One of the big ones is the Weather Surveillance Radar 1988 Doppler, or WSAR-88D. There's 160 locations of these S-band systems around the country and around the world, actually. Another system is the Terminal Doppler Weather Radar, or TDWR. There's 45 of these C-band systems around, and while we do help with some of the support, the main user and maintainer of these systems is actually the FAA. The final system that we help maintain and work with is the NOAA Profiler Network, or NPN. These are flat panel vertical radars that point up towards the sky. There's 4 of these, and they operate on the UHF band. For the rest of the talk, we're mostly going to focus on the WSAR-88D because that is our main system that we have around. At the Rock, there's 4 different branches that all work together to make sure that these radars are operational and keep running and maintained all the time, all day, every day. In the engineering branch, where Autumn and I work, we help provide lifecycle hardware, software systems, and radar product improvement support. So we do things from coding to networking and things of that nature to make sure that everything is going fine from that standpoint of the instrument itself. The field requirements branch helps us on the downstream part where they make sure all the products that we make are actually readable and usable by people in the field. So they check any of the emerging technologies that come out and make sure that they can be incorporated into the system for operational use. The operations branch is where things like our 24/7 hotline work. And also, they have expert technicians that can go out to any of the field sites whenever they need requests. There's local technicians at each place, but they also have our expert level help if they need it at the ROC here through the operations branch. They also have the test team that makes sure everything is tested thoroughly before it goes out to the field to make sure that there are little to no problems when anything new goes out. And the program branch helps us with everything from technical drawings to documentation for all the other things that are going on with the radar, the different components. Without these documents and things and the software builds and things in themselves, then we could not have reliable support whenever things go out to the field. With all that said, there is a variety of backgrounds and talents that all work together at the ROC to make sure that the systems keep going and all the missions are met. So we might be meteorologists by degree and stuff, and there's some engineers that have some degrees, but there's also technical writers and IT support and things like that. So variety from degrees and no degrees, we all work together. Otherwise, it wouldn't get done. And as we mentioned, we really do everything from beginning to end. We make sure it goes up. So for example, let's build a radar. After the ground grid, you have a tower. And on the side, you might start building the radome. Looks kind of like a little eggshell. And then you put some stuff on top of the tower and put the dome on there. And you have to put the dome on top first before you assemble the antenna because the antenna is quite large. So where are these things actually located? As we mentioned, they're located quite literally all over the country. There's quite a few in the lower 48, but we also have several in places like Hawaii, Puerto Rico, Alaska, Guam, and some of the air bases, such as in Kadena in South Korea. So what is a weather radar? Some of you may be familiar, but let's go over it in a little bit more detail. Well, radar is actually an acronym that stands for radio detection and ranging. And the idea is that a signal is sent out from an equipment that, like a radar, and it hits something, some sort of target, and it tells us how far away and where that target is. It can also tell us what type of target it is. Is it liquid water or is it frozen ice crystals? Or maybe it's metal from an airplane or a building. Generally, the radar instruments are on the radio or the microwave part of the frequency spectrum. So if we have the whole spectrum here, generally the weather radars are going to be down on this end with some of the longer waves. But let's get into a little bit more detail about the bands. So here's an example of some of the IEEE definitions of the bands. As we mentioned earlier, the MPN is in the ultra high frequency range. So they have rather longer wavelengths, which is why they're up at this part of the listing. We don't have any weather radars that we deal with in the L band or long wave, but we have quite a few in the short wave, which is where the WSR 88D operates. So these are slightly shorter wavelengths than our UHF. And then the TDWRs are in the compromise or commercial band, known as the C band, and have even shorter wavelengths than that. Now, most of the WSR 88Ds are all in the S band because they have the least attenuation through rain with good resolution. If you pick something like a C band, you might get more resolution, but you'll lose definition as you go through something like rain. So you'll start losing signal behind something like a rainstorm. And that's why S band is used for the WSR 88D. So let's go back a little bit in the history books here. How long have we actually had weather radar? Well, weather started being detected on the basic radar chain network systems that the British developed back in World War II. It's that nice little jokes that goes around of, oh, how come they can see us so well? How can they see the planes coming? Well, we fed all the soldiers carrots, and that's how we can see them. It definitely wasn't this advanced radar technology that we have. So a little bit of scientific collaboration, and people bring it back over here to the States, and they start to develop it for weather. And by 1959, they started putting these in certain places, and some of the major cities and major airports started to get this weather detection instrument. A few more advancements in technology and design techniques and things like that. Forget just getting regular signals, how not. We could also get velocity. So we get the WSAR 88D, which is for the Doppler. And that went out starting in 1992 and is still running strong today. So we had a lot of improvements from the beginning with these sort of echoes on a scope here, where, yeah, we can see things. They clearly are an echo of something. But now we can get real intense looks inside of the storm to know what is going on in more detail. Well, they've been running since 1992. How come is that? How come we don't just swap these things out every so often? Well, the whole equipment isn't necessarily swapped out, but the overall design is upgradable and maintainable because most of the smaller parts can be. So when motors fail or we need a new computer system or something like that, you can swap them out and keep the instrument going without having to build it from scratch. It was also designed to have dynamic scanning control, which gives us options to keep it relevant for any upgraded techniques and technology we learn about the weather. We need to scan in different ways. Well, we can modify the radar to do that. Around 2013, everybody got the dual pole upgrade, which means that we got more information, not just from one direction, but two, in terms of getting horizontal and vertical data and information about what the weather is seeing. And they had to add hardware equipment to do that, but the overall base equipment was usable. And of course, we have people like us still helping to make sure that constant updates are going out for anything new, security updates, making sure new science gets out there, or making sure that any problems or bugs are fixed and things like that. So between the hardware side, the networking side, there's constant updates going out to make sure that the equipment keeps going. There's a variety of different tower heights. If you see them around, go, well, this one's taller than that one, and mine looks different than that. But it's really mostly just the tower height. And they have everything from 5 to 30 meters. So for example, Frederick's around 10 meters because there's really not that much in the way to block it. So that can be a much shorter tower because of the visibility it has. But Seattle has a lot of tall trees, so it needs a much taller tower to get better visibility to detect the weather. And one way to actually tell how tall a tower is when you see it, well, you can just count the stairs. Each staircase is 5 meters. So Frederick's at 10 and has its 2 staircases, while Seattle has 6, getting all the way to 30. So let's talk a little bit more about what is at each of one of these radar sites. There's a few buildings that are usually associated, not just the visible tower that you might see. The front building that you might see here is the radar equipment shelter, which has a lot of really important critical equipment, such as the transmitter, the radar data acquisition unit, and the radar product generator. There's also this building here, which is the transition power maintenance shelter, which is a very critical component in terms of something that usually the radar might get power from your local utility company in the area and things like that. But if that power goes down, then it needs to make sure it seamlessly stays up and gets information from the generator shelter nearby. So those two pieces of equipment go together to make sure that the radar keeps running in the case of an emergency. Of course, the tower and the radome is usually quite visible to make sure that it gives us that better visibility for detecting the weather. And inside is the antenna, which is a rotating parabolic reflector that actually sends and receives the signals we need. So let's take a little jaunt upstairs and see more inside the dome. Of course, most of the dome is filled with this giant 28-foot diameter dish, and it can be moved around and up and down, which is very helpful for things that we need. Most of the time, it spins around like this. So the left side of the picture shows the front part of the curved dish, and the right side of the picture is actually the feed horn that sends and receives signals off of that dish. It's mounted to a large pedestal that holds all the necessary equipment, such as the motors, the gears, and things like that, to make sure that it keeps moving. And it's geared so well that it only takes one person to easily move the antenna around and up and down. And of course, because it's rotating, you have to have things that make sure it can come through when it rotates around. So it's engineered well to make sure that nothing gets hung up or snagged while it's rotating. So let's talk a little bit more about that sampling. Why do we want to do both around and up and down? Well, let's say we have a storm over here. Storms have vertical structure. At the surface, they might be mostly water, but as you go up, it gets colder and you might get more ice crystals and particles going into that. And you want to see how the storm is developing based on those different characteristics. So yeah, we make plenty of scans just at some elevation to full sweep around, see how it's going. But you can also scan at multiple angles to get an idea of the total volume of the storm structure that is happening there. So having that capability means we can see more of the features and detections in real time. Most of the scanning strategies we have give us an update every 5 to 7 minutes. And you can get lower levels updates more quickly depending on the sampling setup that you use. So let's talk some more details about processing the signals. So we have it the receiver, and you go here, you get the mixer and things like that.
No, not like.
Okay, so all right, we'll talk about it this way then. So we have our radar, and the storm low pops up over here. So starting from that equipment shelter we mentioned earlier, a transmitter sends out a very strong signal. It's a lot of energy that goes out to try to detect any target that it could see. Anything that comes back to it is received through here back into the equipment shelter at the radar data acquisition unit, which is then sent to the radar product generator, which makes things such as the base data and a bunch of derived products from that base data, such as daily velocity, some rainfall rates, hydrometeor classification, and things like tornado detection algorithm products. A little bit more detail about what a radar sample really is. Let's say we have a distribution of raindrops, because weather is a collection of a bunch of little targets. It's not just one point target, it is a lot of little targets. So the feed horn will send a signal and bounces off the reflector to make a straight beam, kind of like this. And it does that repeatedly and sends several beams in a row. And it gives us a nice little sampling frequency that we send out for pulse information. And like we did with our practice exercise, we can see there's little short bursts and then a listening time in between each of those pulses. Something is reflected off back into our antenna, into the feed horn. And then we take an area and find out anything that is in that area. We call this a resolution volume because it's just an area of airspace that we're trying to figure out what is all contained within this area. Again, it's not just one little point that we detect, it's quite a few. And so that's what we call a radar range bin or a resolution volume. Now I'm going to hand it over to Autumn to talk some more about the products.
Thanks, Lindsay. All right, well, now that we know a bit about what radar is and how it works, well, what kind of information do we get from it and what does that look like? We have three base moments. We have reflectivity, velocity, and spectrum width. We're going to start with reflectivity. But first, we're going to look at this case and orientate ourselves a bit. We'll be looking at this case for several examples. So here in the center, you have the radar, and then out here you have all these concentric range rings. Now, this case is in 2019, and it's Hurricane Dorian, which you can see just off the coast of Florida here. And how do I know where the storm is? Well, as I mentioned, this is reflectivity. This reflectivity is the strength of energy that is returned to the radar, and it's measured in decibels relative to Z, and Z is a parameter that's related to precipitation. This is the most commonly seen type of radar image. Whenever people say radar, this is usually kind of what they think of. And reflectivity shows us location and the intensity of the weather. So these lower values are less intense, and then these higher, more colorful values are going to be more intense. So in our example here, you can see that we have some higher values closer to the eye wall and out here in the rain bands, and that can indicate that there's more convection going on there. Next up is velocity, specifically Doppler velocity. And that is the power-weighted radial estimate of target motion. Why is it power-weighted? Well, that's so that we don't see a bunch of extra background wind stuff going on. So that way we only see the targets that we really want to. It's measured in meters per second. And the radial part of it comes from the fact that it shows the wind speed and direction only relative to the radar. So we can only see winds that are blowing towards or away. Anything that's perpendicular to the radar will typically show up as this kind of like grayed out color. Conventionally, winds that are moving towards the radar are going to be in cool colors, and away from the radar will be warm colors. Now, what's this weird purple ring right here? Well, that is range folding. So we mentioned earlier that we send out multiple pulses. So if we send out a pulse that hits something far away and there's another pulse that hits something a bit closer, and they come back at the same time, the radar has no way of knowing where that signal originated from. It's very ambiguous. So in that instance, we just paint it purple. Finally, here we have spectrum width. Now, spectrum width is the variability of the velocity estimates, and that's also measured in meters per second. Now, remember our resolution volume that we talked about, where one bin contains multiple targets. So essentially what we have here is we're trying to figure out within our bin kind of like what all the various velocities are in there. And that will tell us or help us estimate the turbulence in the field, from less turbulent values to more turbulent values. So let's look at our example. We have some higher values here, closer to the eye wall, which isn't too surprising. And then we have more turbulent values out here, kind of in the rain bands. Now, if we remember our reflectivity earlier, that kind of corroborates with the higher values we saw there. So that's why it's kind of important to use multiple products, multiple base moments in order to kind of get a full picture of what's going on. And again, we still have our range folding here. So we also have dual pole variables, as we mentioned with the dual polarization upgrade. We have ZDR, rho, and phi. And we'll start with ZDR. So with our dual polarization upgrade, rather than just sending out one beam, we send out two, one horizontal and one vertical. So that's the differential reflectivity here is the difference between that horizontal and vertical power. It's measured in decibels, and it shows us the shape of the targets. So usually whenever you think of raindrops or whenever they're depicted as little tears, but they're actually more of this kind of hamburger shape due to air resistance and surface tension. So they're usually wider than they are tall. So anything that's closer to spherical and ZDR is going to be kind of more of a zero value, while anything vertical is going to be negative and horizontal will be positive. Most meteorological targets are horizontal, so that's why there's more of a gradient here. And if we look at the values here, we can see that there's some larger drops here in the hurricane. And then if you look over here towards the radar, there's all this really high horizontal values. Well, that's going to be stuff like maybe bugs and other kind of clutter that's going on. This really bright value over here is probably birds, because birds in a radar cross section are definitely going to be more horizontal than vertical. Next up, we have rho, which is the copolar correlation coefficient. And that is the measure of similarity in behavior between horizontal and vertical signals from pulse to pulse. And we can kind of visualize this with vectors. So we have a horizontal vector and a vertical vector. We do some math and put those together, and we can visualize it like this here as being our correlation coefficient. And that is also why it ends up being unitless. What does this actually tell us, though? Well, this kind of helps us estimate how similar the targets in the radial are to each other. So things that these lower values are going to be less similar to each other, and the higher values are going to be more similar. So if we look at our example, we can see out here in these rain bands that that's all pretty uniform out there. Looks pretty similar. But then here, while we get in the main body kind of towards the eye wall, it's all less similar. There's like slightly lower values there. Well, why might that be? Well, we have our radar here. As we kind of mentioned, it sends out the beam, and then as the beam goes out, the Earth curves away from it. So the farther out you are, the higher up in the atmosphere you are. And since it's colder higher up, these might indicate ice crystals up here, where all this kind of mixing might be going on. Finally, we have phi. And phi is the differential phase, which is the difference between the horizontal and vertical two-way propagation phase shifts. Well, what does that mean? Now remember, we have our horizontal and our vertical waves that are going out. And remember, they're waves, so they have a phase. And as the waves interact with the atmosphere and with the targets, they attenuate, they slow down, and the phase shifts, which is kind of how we measure that. So let's kind of relate this back to our correlation coefficient. We have our vectors. Here's our correlation. The differential phase is simply the angle here that we measure, and that's why it is in degrees. What does it actually tell us? Well, it gives us information about the particle shape and the concentration of particles based on kind of how that changes. And it's measured like by the radar. We have like a reference degree value, usually around 60 degrees. Anything less than that is going to be more vertical. Higher than that will be more horizontal. Looking at our example here, we see we start from the radar and we go out, we see these values increase. This is a cumulative kind of product. So if it went farther out, then we would see higher values even. This can be kind of difficult to interpret on its own. So we have a product derived from this that is more commonly used that we'll look at later. Pardon me. So we've gone over kind of the data that the radar has. So what can the radar actually see? Well, we can see tornadoes. Here's an image from Kansas in 2016. We have our classic supercell structure and the reflectivity on the left. You can see the hook echo here, kind of towards the center. And then over on the left, you can see our Doppler velocity, and you can really see the couplet as it moves along. So remember, we have our red values that are away from the radar and green that are towards. Whenever you have them in very close proximity like this, you can see how that would indicate rotation. We can also see hurricanes, like Hurricane Maria back in 2017. And this is as it was devastating Puerto Rico, and it also devastated our radar. We actually lost this radar to the hurricane, but it has since been rebuilt thanks to the concentrated efforts of technicians at the Rock and along with help from our agency partners. It's always humbling to be reminded that the instruments we use to detect the weather are not immune to it. We can also use it to see like derechos or severe wind events. Now, this is a radar mosaic, which means we've taken a bunch of reflectivity images here from several radars and stitched them together. It helps us kind of see the scope of events like this in particular, which this one tracked across hundreds of miles over the course of about 12 hours. This event was pretty severe. The strongest wind gust that was estimated was around 140 miles per hour, which is stronger than some tornadoes. And it cost $11 billion in damage, which is not insignificant. This kind of goes to show just how important it is to have radar data so that people can kind of see what's coming and prepare for as best they can. And sometimes weather causes problems as it blows through very quickly, and sometimes it causes problems by sitting in one place and not moving ever. Like in Fort Lauderdale this year, where they got like 24, 25 inches of rain in a very short amount of time. So you can see here in reflectivity how this big red blob just sits here and doesn't move. And they added to the fun because over here in the velocity, you can see a small little spin up, a little tornado that occurred just briefly. Over here in ZDR, you can see these high values that indicate large raindrops. And then kind of as the storm evolves, you can see how that works. And this is the specific differential phase, which is the derived product from phi that I mentioned earlier. So that is created by taking the gradient of phi, which basically just shows us where the areas of interest are. So the higher the values here, the more that the rain rate and the drop sizes are increasing. And this product is frequently used for precip events like this one to get a better idea of what's going on. And dual pole also helps us kind of differentiate between what is weather and what is not. So we can see here in our base moments, we have reflectivity on the top left and velocity on the top right. And sometimes it can be kind of difficult to differentiate here what's actually weather and what's maybe an outflow boundary or something else. But if we look here at our high ZDR values and our low correlation, which means not very similar, then we can see that there's actually quite a lot of dust and biologicals going on, kind of being blown around by the thunderstorm outflow. Now we can also see wildfires if they get pretty big. So this was a fairly significant one from 2017. You can see here, here, and here, a little bit uncomfortably close to the radar. As the fires grow, of course, they burn things, and the ash and smoke gets lofted into the atmosphere, and we can detect that. And you can also kind of help tell that it's smoke and not something like rain, again, from these high ZDR values, which might be like large ash flakes, which would be kind of weird and bulky shaped. And then they're not very similar because they're all going to be very different from each other. And this is what our correlation tells us. Not only can we see ash from fires, we can also see ash from volcanic eruptions like Mount Redoubt here in Alaska. So you can see here's the volcano as it erupts and out it goes. And we don't have too many radars that are close to volcanoes. But whenever something like this happens, it is good to know that we can see that. And here we have an interesting case that just kind of shows off the sensitivity of the radar. So this is in Colorado. And so the day before this, they'd had a big snowstorm. And then the next day they had a lot of high winds. And those high winds blew the snow off the top of the mountains and created all these really, really light returns. Now, sometimes the field, the weather forecast offices will call into our hotline and ask for help kind of interpreting if there's something weird that they're not really familiar with seeing. And this is one of those instances. So sometimes weird things just happen and we're there to help support in whatever way we can. Now, I've mentioned biologicals a couple of times, and that pretty much it is what it sounds like. It's bats, birds, and bugs. And so in this case, we're looking at roost strings. So you can see in all the products that are shown here. And this is specifically roost strings from the purple martin as it migrated. So basically they'll kind of sit in their trees overnight, and then in the morning they all just disperse, and it's always pretty neat to see. And so you get scientists that study birds and bugs that will use radar data in order to track migrating populations. So we mentioned a couple people who use radar data, but who else uses the data? Well, the government, for one. Everywhere from a local government, like the local weather forecast office, to city managers who might use it to help determine where to close off roads or to get snow plows or to sound tornado sirens, which they're responsible for. And then regionally, we have the river forecast centers, which take care of hydrology for their regions. And then also they forecast for the any kind of river changes that are going on. And then state departments of commerce, which might use radar data to help update their statewide like traffic advisory maps. And then of course you have the national government, and this is just a small sample of kind of the most frequently used like organizations. We have the National Hurricane Center, the Aviation Weather Center, the Storm Prediction Center, and then of course air traffic control, who's going to use radar data to help planes take off and land safely, and then military operations, who also need radar data. And this is just a small sample really of all kind of government organizations at every level that use radar data every day to help accomplish their mission. But of course, they're not the only ones. As PBS would say, viewers like you also use radar data from your mobile app, and then to using it for outdoor event planning. There's companies that specialize in nowcasting for big outdoor events like sports and music venues. There's academic institutions so that they use radar data for research for various things. And of course, your local news stations. And the important thing is that radar data are actually free to the public. So as the Radar Operations Center is under NOAA, kind of the NOAA umbrella, and part of NOAA's mission statement is that weather data be made freely available to promote public safety. And the ROC is proud to contribute to that. So where can we find more information? Well, you can find radar data at your local WFO page. And if you don't know what that is, you can just go to weather.gov and type in your zip code or your city, and then it'll come up with your forecast page, and there should be a link. This one's from Topeka, and they have a little link over here where you can get your radar data. And if you don't want to look at what's going on right now, you can look at stuff that happened like 10 years ago if you want. So the National Center for Environmental Information actually archives radar data, and they have it as far back almost as 1992 when the whole system went out. They also have a viewer, so once you've downloaded your radar data for free, you can view it using the viewer that they have. Again, we also mentioned there's a whole bunch of mobile apps out there that you can use to view weather data on your phone. Some universities will also have like radar data that you can access, especially if they have a meteorology focus. And local news stations, they will use the local radar, and sometimes they also have their own. And if you want to learn more in general about, say, meteorology, you can schedule a visit to your local forecast office. They usually are happy to do tours. You can visit the Weather Decision Training Division website, and that's where forecasters go to learn more how to interpret the radar data. You can check out the NWS Jetstream page, which is a really great resource for just kind of general meteorology information. And you can view the ROC website to learn more about us, And of course, you can always visit your local library. If you want to know more about engineering, you can consider doing classes through kind of local VOTEC. And some places even offer cross-listing while you're still in high school and beyond. And along those lines, you can look for community college courses. You can also explore internship or volunteer opportunities, and you can look for courses online. And again, you can visit your local library. Your librarians are going to know a lot about where to find a lot of these resources, and it's good to help. There's a lot of information out there, so it's really good to have someone who kind of knows how to get you started. Well, so thank you very much for listening to us, and we'll take questions.
All right, thank you much, ladies. We really appreciate it. Let's see, I think we have a few questions that have popped in. Does the rock provide data interpretation support?
If a field site will call in and ask about how to interpret the data, yes, sometimes the hotline will interpret support, kind of like Autumn mentioned with the blowing snow case, where somebody in the field said, hey, what is this? And they called the hotline and they said, oh, it's this, and they tracked it down. And sometimes they will do things like the replay data to know if the derived products, such as precipitation rates, are accurate and things like that.
All right, another question that came in. For radar, you have for the FAA, how does it interface with airport radar for approach, landing, and ground control?
So you're asking about the TDWRs, and of course we are definitely not the FAA experts here, so that might be a separate question to go look up externally. But I know that they use the TDWR specifically to help look for things like microburst and downburst detection. So they built those radars specifically around certain terminals, which is why it's the terminal Doppler weather radar, to help detect that. And so I know that they have their variety of, yes, because they'll have like 5 or 6 different radars of various kinds between their point radars and other types of atmospheric profiling radars they'll have at an airport. They have the TDWR and the WSR-88D information to give them a full scope of weather for each airport.
The question was, how does it interfere?
Now, how does it interfere?
Yeah.
I thought it was.
Oh, interfere. Yeah, sorry.
I don't. No, so I'm not really sure in terms of how it would interfere with other types of radar. I guess we're asking about such as the local scanning radars they might have for point detection planes.
The question really kind of went around, what bands are you using versus they're using?
Oh, okay. Okay. Well, we have like the C band versus the S band. Like the TDWRs have the whole separate band, partially kind of for that reason, I imagine. So we don't have as much interference with each other.
That's correct. And even the 88Ds, they have very, very specific frequencies that they are set to. So anyone that's close by each other does not interfere with each other. Because if you have two WSR-88Ds nearby, they can interfere with each other if they're on the same band. But the TDWR, because it's in that C band, is far enough away from the S band that they usually do not interfere.
Okay. All right, the next question that came up is how does a tornado show up versus wind shear?
Ooh, well, usually with tornadoes, you can see, can we go back to that slide?
Sure.
I don't know which slide that was, but just go back. I think it's like, yeah, I'll just go back to here. So let's go back to our tornado example.
I think it's going to be closer to like.
There we are. So usually whenever like we have a tornado, it's usually that those kind of differences are really, really, really close together. And versus shear, it's, so let's see, like you can kind of see that there's different stuff going on. Let's see, we're approaching. So, I mean, really, it's one of those things that you kind of learn by experience in some ways. And also just by watching, like it's loops essentially too, because you can really see the rotation here as it moves along. And then with shear, it usually doesn't quite, it just doesn't look the same. It's can be hard to like really.
Yeah, it does have slightly different characteristics. Usually the tornadoes are a much tighter
Yeah.
shear couplet because it is shear.
Yeah,
here,
it's very, yeah, it's
but
definitely sheer.
But it's much tighter in a location, area, and range. And sometimes, again, we mentioned that there's different vertical tilts, and you will use the vertical aloft to see what that shear profile is changing.
Yeah.
You can also see some of that. They have a vertical profile product.
Yeah,
that you can help see. It has like wind barb pictures on
it's this little graph, and it has all these wind barbs in different directions, and it's kind of like time based, so you can see how it evolves, how the wind field evolves over time and also in altitude. Yeah, we didn't have any just straight shear examples with our velocity, but those are usually, you can, like the resources we listed, you should be able to find an example somewhere in there. Probably WTD would have some good examples of that.
Right. If we had not shown the full mosaic for the long derecho to get the full picture of the derecho, there would be lots of shear and wind gusts in that. Actually, in the dust.
Oh yeah, yeah, you can see a good
with
outflow.
the outflow.
Mm-hmm.
We can see that wind profile change as it moves across.
Mm-hmm. Yeah, so you can see here is the actual outflow boundary as that kind of evolves as it pushes out.
All right. Let's see. We have another question. Derecho. Where does the term come from?
Ooh. That I'd have to go back and look. That's some weather service history we have to go back and look through in terms of. I know that the term probably came around in initial use, I think, in the 70s.
Yeah.
But it was kind of isolated because the place that they normally happen is in, the Midwest sees them basically every year. They are a major weather concern in parts of the country. But again, it's hard to see the full picture without a whole lot of instruments to see it. So by the time you start getting satellites and more widespread radar coverage in the 70s, you can just see how big and how widespread they are, because the derecho has to have a specific damage over a certain amount of distance parameter to be counted, as opposed to just a normal squall line or a straight line wind event. They have a really specific threshold for that the Weather Service defines to call it a derecho. But I think it was about as early as the 70s that it first came around, and then it has really picked up with the advancement in technology.
All right. Let's see. We have another question. Do you have a counterpart organization in Canada, and how do you interact with them? Same for other parts of the world.
Yeah, it's interesting because we're actually going to a conference next week where we will probably see quite a few of these groups from around the world. And yes, there is a group of them in Canada, and we've actually coordinated with them in the last few years. They upgraded all of their radars to S-band, and they coordinated with us in terms of how to do that with the network. They went from C to S-band because it is just better for things like the strong severe weather signals we get in parts of the world here. A lot of other parts of the world might be using C-band because either they're isolated smaller areas or things like that. But yes, we work with places like Meteo France and the UK Met Office, and I think it's EEC who it is in Canada.
All right. Another question is Doppler radar. What is the difference between a radar that has Doppler and another radar that does not have Doppler?
Well, the Doppler radar can see the velocity data and things that don't, like the other radars that don't. So our original like 57s, they couldn't see the velocity, and the Doppler, that's what that gives us, and that's named after, I guess, the Doppler effect, which is, whenever. So the classic example is whenever you have an ambulance go by, and it has like a different pitch as it goes by based on how the sound waves are compressing and then expanding as it passes by. So that's kind of a similar principle to why that's called the Doppler.
And the way that the sound waves are coming at you and changing is just how it's part of the way multiple pulses are sent out from the system. Using the multiple pulses actually helps with that estimation of the wind as it goes down.
All right. Another question for the WSR 88D. What is the maximum range that it could see?
The maximum range is about 460 kilometers for reflectivity and 300 kilometers for Doppler. Because of the Nyquist trade-off, the way it's just a normal standard physics issue that we have, there's always trade-offs in radar. So the idea is that you can either see really far in range, but not get a lot of detail in your wind, or you can get more detail in your wind, but not see as far out. So we have different scanning strategies to balance those out. So we'll do one scan to see really far out in range, and we'll do one scan to see better wind speeds.
Okay. Another question, is the WSR 88D a pencil beam radar or wide beam radar?
It's a pencil beam radar. The beam width is approximately 1 degree.
Okay. Peter, do you have any other questions on your end?
No, I don't.
All right. Well, thank you much. I don't see any other questions that have come in. I really want to thank Lindsey and Autumn for the presentation tonight. It's very interesting, very informative. I hope everyone has enjoyed this presentation, learned a lot about weather radars and the Radar Operations Center. Thank you much, and good night.